Okay, so we spoke about complex numbers, and then we said a complex number was the phasor. Right? The only thing you need to understand is the complex number part you already know, and some of you don't know, and then we have to set up a date for that. See, when I say we have to put a date, when I walk out of this door, I have forgotten it. Yeah, we have tons of things in our mind. By the time I hit the door, even before I hit the door, I have forgotten it. So it's up to the people who, I guess, need somebody to come and do complex numbers, to come and talk to me and make sure that I make the, I guess, necessary arrangements for you to, I guess, know complex numbers. I think I did upload something on the net which explained what complex numbers are. Did you see that? No, you didn't. So go here and look. There was some sort of videos I uploaded on complex numbers, I think. So just go look at that. Essentially what we said was, what you mean by a phasor is it has an amplitude and an angle. Then we said that, when this changes, the angle changes, and I showed you how this sinusoidal waveform for a particular angle can change when the angle is also changed. Then we said that these three signal waveforms can be written like this, which I'm sure you would have seen already. And then from that, I brought you into finding out AC equivalent circuits for the resistor, for the capacitor, and the inductor. And this little thingy that I drew here is what is called the phasor diagram, which means if you look at voltages and currents in the circuit, the plot of its magnitude and the phase is called the phasor diagram. See, here you realize, if I look at the two, so I will do this again. So I think that's where we stopped, right? And we showed you a very simple example. We are going to do a second example, and that's where we stopped. Okay, so let's start from where we stopped. So I said, so if you take a look at a resistor, you are going to realize, okay, if it is a resistor, then you realize V in of t, or maybe I call it VR of t, is equal to V max of sine omega t, and you write IR of t, which is of course the Vn and V, I guess VR, and you can write this as plus minus, that is VR, and that is IR, right? And this is the resistor value. It was written as some I maximum. In fact, we also said Vm over R. This was sine of omega t, right? So if I want to draw the phasor diagram for this, I have to convert this into R theta format. And then you also know, of course I didn't do it here, but you also know that if you are bringing from here to this point, you have to make sure it is the RMS value, right? It is RMS that you use as the magnitude, and the angle here, because there is no angle, is equal to 0. So over here, what it is Vm over, right, root 2R, and you realize Vm over root 2 is the RMS of the peak value Vm, and again the angle was equal to 0, and then you realize now I can plot the phasor diagram, voltages and currents and so on. So I have an x-axis and like y-axis. You realize you have a magnitude and then you have an angle here, right? Of course, these don't have any axis marks, because why? You are drawing it in terms of r theta. So here you realize VR is what? V max over root 2, which is some sort of index, some value, with an angle of 0. So I draw a straight line like this. That is VR. Because why? It has a certain amount of magnitude, which is equal to Vm over root 2, and then it has an angle 0. Then on the same side, I have IR. Again, I realize it is an angle of 0, but this magnitude is a little smaller than that. I don't know if it's smaller or not, but I'm assuming it is smaller. So that is IR. That is a phasor diagram of a simple resistor. Then in the same form, you can also do the same thing for an inductor. Right? For an inductor, V is, right, VL of t is equal to, what was this? It should have been sin omega t plus 90, right? IL of t, right, would have been this Im times sin of omega t. How much was this? This would have been L omega Im. Yes? I don't know. Go back to your last note and see. Right? So now you have a two signal. First of all, can you check whether this is okay? Is it okay? Check somebody. Yes, is it okay? Yes, fine. Okay, now you got to draw the phasor. What do you have to do when you draw the phasor? Convert this into r theta format. So this is equivalent to base L omega times Im. There's an angle of 90 degrees. Right? Then here it is equal to what? It's just Im with an angle of 0 degrees. Now we got the r theta format. Draw the phasors. How do I draw the phasors? Draw the xy. First take this one. You have a certain amplitude, but it with this angle which is 90, and you know that the angle increases in the counterclockwise direction. So that is going to be this is VL, which has an angle of 90 degrees, and this amplitude would be what? Basically L omega times Im. Now you realize, if your inductance is not changing, which is L, and I is not changing, Im, whatever the maximum value is not changing, but here you realize in the equation this magnitude can change with the frequency. Alright? Yeah? You realize it changes with the frequency. This is your experiment that you're going to see. Right? Now, all this time you were very comfortable with using, I guess, resistors, and you realized that you gave a certain input voltage. That input voltage was split between all of the resistors. So, any time you find out this voltage which is across this particular resistor, you realize it is smaller than the input voltage that you apply. Yes? Voltage add up to give you this. All of a sudden, you can see inside AC theory that you give maybe 100, I guess, right, 100 volts as your input signal, but if you go and look at this voltage across your inductor and the capacitor, that can be more than 100 volts. Right? You're going to realize that. It's okay, because why? It is 100 volts with an angle. Right? It's not just 100 volts. Because if there was no angle, you should have all these little voltages simply adding up to the input voltage. Here, it may not be the case. So we know that this is case. Then you have to draw this one, IL. You realize it has some like maximum. So if you look at this one is multiplied by L omega. I am thinking it's greater. It doesn't have to be greater because L can be 0.1. Right? Well, let's say, we don't care what it is, but we realize that this is I of L. That's the phasor diagram of an inductor. Phasor diagram of an inductor. Then also, you can do the same thing. You can do this exercise, the same exercise for a capacitor. You can write V of Ct is equal to, I guess, V max times sine of omega t, and IC of t is equal to Vm over c omega sine omega t plus 90. Can you check this and see? Even with 100 years of teaching, I can get this wrong. Right? Because why? I don't keep that in my mind. I don't have to. Is it correct? Check it. Is it correct? Yeah, I never keep these equations in my mind. What's the point? It's like marbles that if you start to do that. What happens if you got more and more marbles? Some of the marbles are going to drop off, fall off. You have to build a chain of marbles, attach them with a string, then you can have any amount of marbles and you can hold on to it. So I know how to obtain it, but I don't know what you're going to get at the end of the day. So is it correct? No. Okay, what do you get? Huh? VMC omega. Good. There you are, see? So we got this. Now what we got to do is to convert this into r theta format. Again, realize, ladies and gentlemen, I should have put here root 2. You understand that? But in all your questions, unless I give you a sinusoidal signal, all the others are already in RMS form, and I'm going to show you what RMS is also. Right? So here I am going to get Vm over root 2 with an angle of 0 because there is no angle here. Here it is Vm times capital C omega over root 2 with an angle of 90. So now I can draw the phasor diagram. Here, this is Vc of t will have a certain amplitude, but angle is 0. So this is Vc, right? You probably would not put Vc of t, right? Just Vc. Then over here you have this as I, and that is I of c, right? You can put t, it's okay, but Vc. I see. So it has an angle of 90 degrees starting from, and you always take that as your reference, right? That as your reference. So that was what we understood, and that's what we in fact learned. So let me do a question for you. Let me see if I have I want to first of all show you if I take a simple network, how am I going to handle it using the, network rules. Right? Norton theorem, Thevenin theorem, all kinds of other theorems. How are you going to apply it to a simple AC circuit? So here you are. This is my AC circuit. Right? There is a resistor here. There is an inductor here, then there is a resistor here, there is a capacitor here, and a current source here. Right? There is a current source. So here this is E plus minus. This is 12 volts with an angle of 0. Immediately if somebody gives it to you in R theta format, this is in what? Already in RMS form. So if somebody says you got 12 volts with an angle of 0, what it means to you, if I want to draw a sinusoidal signal, is this is what? 12 times root 2 sine of omega t, some frequency, plus angle of 0. That's what it means, right? If I want to draw it. Then okay, then they have stated R to be, so this R1 is given as 0.5 kilo ohms. Then X of L, now remember X of L is what? Okay, I'll write it out also. This is 10 kilo ohms. They have given you what? Rather than giving you the inductance value, if they gave you the inductance value, right, the actual actual reactance would be what? Capital L times the transfer frequency, L omega. They have done that calculation and given you the final value. Right? Most of the problems that we are going to solve, we would not give you the inductance. We will give you the reactance, which is what? So if you take yourself I guess inductor, you will have the reactance to be what? Basically L omega. So if I give you L and if I give you the frequency, you should be able to find this L omega. That is this. This is XL. Then if I give you a capacitor and the reactance of that would be 1 over C omega. So if I give you C and a frequency, I can calculate this. That is XC. So I will give you this also. This is X of C, which is equal to 5 kilo ohms. R2 is 2 kilo ohms. Then I here is a vector, of course. It is 4 milliamperes with an angle of 0. Here is the ground point. So I am going to show you how this problem can be solved to find the voltage across that inductor VL using nodal analysis. Right? Using nodal analysis. So here, the first thing you are going to do is to transform this whole circuit. Unfortunately, you can't do this kind of tricks, but transform this whole circuit into the AC equivalent circuit. So how do I do that? This is already in the AC equivalent form, R theta format. Here, I am going to take this out. Keep in my mind, all these impedances and the reactances are in actually what? The scale is K. I keep it in mind. Then I change this to 0.5 because you realize R is actually R. Then here, this is an inductor. So I take this out, and I write J times 10. Remember, if it was an inductor, it was JL omega, was the actual impedance, right? Actual impedance, right? This part of it is called reactance. Then if I put in the J to indicate that it is actually 90 degrees offset, then you call it the impedance. Now, had you gone and read the stuff that I asked you to read, you would have already located this in the book. Right? Already located this in the book. And I was told that the book is not available. I was told that the book is not available in the, I guess, the bookshop. I call the guy in the bookshop, he says it is. I don't know which bookshop you guys are going to. Right? Maybe he doesn't know what is there in his bookshop. That could also be a reason. So I called him up again. So he said he's going to call me back in 5 minutes. That was about 2 hours ago. So you want to still searching to see at Boyle State. Right? But here's a good thing. There are some of you who have the book. Can you put your hands up? People who have the book. See, there are about 2 or 3 people who have the book. Then what you have to do is you can, all of you guys are smart people, you can find the e-book online. Right? The chapters are different. But the course content or whatever the content is the same. Check a book. Change the code numbers to chapter numbers to whatever the numbers are there, and I think the rest of it is the same. Once you take out the chapter numbers, the rest is the same. Right? So there you go, you can take it. There you go. Okay, now we got this. This is actually a resistor. So I have to what? Replace it with just the number. Here, this is a, yes, but this is a capacitor. And they have given 1 over C omega is equal to 5K. That's what they gave you. But what I want to put in here is the impedance. What I want to put in here is 1 over JC omega. Right? 1 over JC omega. But this is also equal to what? It's minus 1 over, j over c omega. We showed you this last time. Right? Because why? If I take j to the power 2, it is minus 1. Because why? J is root of minus 1. That you used to call I. Right? So, if I substitute this, what would this become? It's minus j times 5. This is what? Already in AC form. So, which means what? This is an RMS value. A very simple way of doing this is, if they give you the reactance, if it is an inductor, just put j times the reactance. If it is a capacitor, you put minus j times the reactance. That's all. Right? If you don't want to think about anything, but I don't think you should do that. You should think to yourself and say, whoa, this is minus j5 because of that. You may not put it down, write it down, but in your head you see the j's all flying around and then you put it down as minus j5. Don't be like this guy who's just going in and putting j5 without asking anything. Now here, the best method to solve this, is to redraw this circuit, right? Redraw this in that form. Here, redraw this in this form. Don't try to do all the problems using the j's and the minus j's and the angles. Don't do that. Because you are going to, halfway into the problem, you are going to get mixed up. Don't do that. Here's what you do. You are going to redraw this circuit in a simplified manner. Call this E. I don't know, we know what E is. Here, you put a box and you call it Z1. Z is actually the symbol that they use for what? Impedances. Put Z1. Then I will replace all of these with boxes. Z2, Z3, Z4, and that is I. On the side, draw a straight line, write down everything that you have just written. So you write E is going to be 12 volts with an angle of 0. Z1 is going to be 0.5. Z2 is going to be J10. Z3 is going to be 2. Z4 is going to be minus J5, and I is going to be 4 milliamperes with an angle of 0. Now remember, in a question you should track the units. You track the units. If your impedances are in K, right, you have voltages in terms of volts, then the currents are going to be what? In milliampere. You know this. Track that, just like what we did in the DC circuit, you have to track this. Perfect, because why? That is in B, these are in K, and the only current we have is in milliampere. So in fact, units match. Generally, this is the case. Unless somebody who gives you the question is a little crazy, like me, they would mix up the units so that you get all worked up. What is this? Other than that, they generally give you that in volts, this in K, that is in milliampere. So that all of those units match. Now, your problem is simplified. Now, forget about the fact that this is an AC circuit. Now you apply nodal analysis. How many nodes are there? How many? Oh, wait. Let me ask you, what is the smallest number of nodes you are going to pick to solve this problem so that you can find the voltage across Z2? What is the smallest number of nodes that you are going to use so that you can find the voltage drop across Z2? How many? Yes, let's ask this. How many would you choose? I'm not asking the maximum, I'm asking what is going to be the minimum that you're going to choose. 3. nodes included in the, how many? 2. This, okay, fine, and then this one. 2. Because why? We have told you that if you have a resistor and a source, right? Don't put a node in the middle, use it as a branch, because we have an equation that tells you how to find the current. So here you are. No problem, I'll use the same sort of a technique. Same technique I'm going to use. This is a node. See? I don't need to have a node here, because why? I can take this voltage minus that voltage to find the current that is flowing over here. This is a node. This whole thing is obviously going to be a node, because it is a ground of the system. There you are. So I'll put this as node 1, node 2, this is a node 0. Now I write my equations, nodal equations. What are the nodal equations? I apply the Kirchhoff current law to first node. You assume going in minus, coming out, I don't know. Whatever you want to assume. But you got to make sure for each equation you use the same method. So I'm using the ones that are going out, the current that is going out of the node is going to be positive. So I can write the equation V1 here, V1, take away E, see E over Z1 is the current that is going out. Here this is plus V1, take away 0, so this is 0, over Z2. Plus, I will have V1, take away, this node voltage is V2, over Z3 equals to 0. Right? Then I can apply the Kirchhoff current law to node 2. I will have an equation which says node 2 V2 minus V, right, V1 over Z3, V2 minus V1 over Z3 plus V2 over Z4, V2 over Z4 plus capital I is equal to 0. Now you have an equation in terms of V1, V2, right? I suppose, right, rearrange this as V1 1 over Z1 plus 1 over Z2 plus 1 over Z3, right, minus V2 1 over Z3 from here equals E over Z1. That is the first equation. Here I can get V1 over 1 over Z3, right? V1 1 over Z3. I got, right, minus this is 1 over Z3 plus 1 over Z4 times V2 is equal to I. Now I can apply the Cramer's rule to this. But just before I do that, I substitute the Z1, Z2, Z3. Right? I can know now. If you do up to like that point, you would have got most of the marks. Right? You don't even have to work with the complex numbers to get the mark. Up to that point, you have got most of the marks. Then it is algebra. Right? Algebra. If you substitute all of these, apply the Cramer's rule, and you got the answer. Right? Now you realize that nothing is different. Nothing is different except for the fact that what? You have to make sure that the circuit is converted into AC. Which means you need to look at IV and then also the inductor and the capacitor. So let me take, okay, I have the answer, so let me give you the answer to this. So this whole thing, when you turn up, if I look at 1 over Z1 plus 1 over Z2 plus 1 over Z3, right, works out to be 1 over 0.5, Have I chosen the same? Z2, Z3, Z4. Okay, that was it. And then this becomes plus 1 over Z2, which is J of 10, plus Z3, 1 over 2. That works out to be 2.5 2.5 with an angle of minus 2.29. So if I want to find out Z, see, I substitute that here. I know what is Z3, 0.5. So I can find the Cramer's rule and do this. Right? And then you realize that V of Z2 is nothing other than V2, right? V1. See? V1. And that will work out to be 9.95 volts at an angle of 2 degrees. 2 degrees. Go home and try it out. Nothing is different except the fact that vertical into AC. Now if you apply any other rule, like mesh analysis to this, you can pick some sort of load resistance and apply the Norton theorem, Thevenin theorem, all of those things. You would get the same process that you did for DC analysis. Right? Okay. Let me take the same question and show you. Let me take the same problem here, right? Let me cut it out. Right? I think, right? Rather than spending your time taking down all of these things, which you are going to have anyway when you go home, there are some things that I say that I don't put down here. You might want to take those down, right? So that when you go home, you can use this note, right? Use this note, rewrite it, and then put down those statements, right? I sort of also appreciate you taking it down, because once you take it down, you're going through the steps in your head as you write it down. But in the meantime, also you need to give it some attention, right? Not only putting it down, writing it down. Because if I ask you a question, you don't know, where is it? So you have to know where you are, what you are taking down. Okay, let me go back and show you. Now, if I am asked, right? If I am asked to find let's say if I am asked to find the Thevenin equivalent circuit of this by taking that as the load. Same thing. I want to just show you how I can apply that to find the Thevenin equivalent circuit. How do I do that? Again, I would do what? I would redraw the circuit, right? I would redraw the circuit by simply eliminating all of the circuit values, and I will replace it with black boxes, right? This I will keep as I, this I will keep as E, right? Then This is where I want to break the circuit, so I'm going to remove this. I'm going to break the circuit from here and look through that. That is my RL. Look through this to first of all find the Thevenin equivalent resistance. Now tell me, if it was a DC circuit, what would your first step be? Eliminate all the sources. What do you do? Short circuit what? Yes. Short circuit sources. I just take a wire and whole thing. Short circuit. Is that it? There are different forms of sources. You got voltage sources, you replace it with a short circuit, so that the internal resistance become empty. And if it is a current source, you open circuit it. Same rule applies. So what do I get? Here, this is what I get. Draw a straight line. This is going to be short circuited. So if it is short circuited, I would have something like this. This is Z1. Right? Short circuited. This is open circuited. If it's open circuited, I will have Z3, Z4, and that's what I got. And I have to find the equivalent impedance here. What is the equivalent impedance? You can redraw the circuit couple of times to flip this here and there, but you understand it is R of TH is equal to Z1 in parallel with Z3 plus Z4. Right? If you can't see it, redraw the circuit. Why? Because this and this are going to be in parallel, so they can be flipped around. So I can redraw this as like that. That's where I'm going to look at RTH. This is Z1, this is Z3, and that is Z4. There you are. That's done. Now I have to find the open circuit voltage. How am I going to find the open circuit voltage? Yes, which method do you think would give me the open circuit voltage easily? Yes. If I put mesh analysis, the advantage is what? You have idea, which means one loop current is already known. I can only find the other, right? So I got to find the loop current. So let me take it to the other side. Copy this whole thing. Control C, Control V. I will erase this. Ground. This is the loop 1. That is loop 2. You immediately realize that I2 has to be I, because there is an independent current source here. I have to apply the Kirchhoff, right, voltage law only to this single loop, and I call this, because there is an ambiguity between these two loops, I call it capital I1, and capital I1 is equal to small I1 take away small I2, and I write the Kirchhoff voltage law to loop 1 in the clockwise direction. You realize this is going that way, so the voltage drop is going that way. This is going that way, voltage drop going this way, this is going that way, the voltage drop goes this way, the voltage drop goes from minus to plus, and that's what we have. So if I write the Kirchhoff law here, E, right, you got, I guess, minus of, you got base I1 Z1, right, minus I2 Z2, sorry, Z3, and you got what, minus of I1 take away I2 times Z4 is equal to 0. From this we know I2, I can find I1. So and then also you realize this is what we want to locate, this voltage. right? And then you realize V open circuit is equal to what? Yes, E, right? You got minus small I1 into Z1. Now you can substitute your J's and the angles and what, right? And you can find the answer. Now remember, you have E and also capital I in terms of theta format, whereas Z is in the rectangular format. So you have to move, I guess, one of them into R theta format, or the other into the rectangular format, right? Find the answer. So that is it. Okay, here. So if I look at Z1, okay, there's no problem with Z1, right? Let's look at Z2, right? So if I have Z1, 0.5, if I want to convert this into R theta format, it will be 0.5 with an angle of 0, because this doesn't have any angle, because R doesn't have any angle, right? So if I want to convert it into rectangular form, it is 0.5, right? If I take C2, right? If I take C2, and if I want to move it onto base R theta format, sorry, I will first of all write rectangular format. It was J times 10, and if I want to move this into R theta format, it will be 10 with an angle of what? 90 degrees, right? Because why? You got A plus JB, and you have, I guess, magnitude of A plus JB being equal to root of, you got A squared plus B squared from your complex number theory, and then you have the angle of A plus JB to be equal to base inverse tan or maybe arctan of B over A. And then if you want to convert this one, which is in the rectangular format, onto the polar format, it will be what? A squared plus B squared with an angle of tan inverse of B over A. Now, if I take J of 10, you realize A is equal to 0 and B is equal to 10. So if you take basically this A squared plus B squared root, you're going to get what? A squared is 0, B squared is 10, it's going to be 10. See, that's why I got 10 here. And then the angle, tan inverse of B over A. Yes, B is what? B is equal to 10, and A is equal to 0. So this is what? Basically, it is inverse tan of what? Infinity, and that gives you 90 degrees. So that's how I got the 90 degrees. Right? Okay, there you are. Now what I have to do, after I do all of this stuff, what I have to do is, I have to say that, okay, that was Z2, this is RTH, and that is V open circuit. I put back the RL into the circuit. So I have brought the entire circuit down into a single source, voltage source with a resistance. Right? Good. You seem shaken up. No? Folks, there was this person who came to see me in the morning. I think it was from Yahoo. And they were saying that some people understand the phasor diagrams. Probably. Right? Do you understand phasor diagrams? So I understand, half of you don't understand phasor diagrams. Because you got hit by this, I guess last week. Weekends, no study. Party. Come Monday, again with the phasor diagram on the base. You can't do this. thinking half of you understood this. If half of you didn't understand, there's trouble. Right? Other half has to crawl, scratch, climb up the ladder to get to this level. Because this is going to come in your exam. I'm telling you, do all the problems, start to send me the stuff so that I can do at least in the revision class. It is not my responsibility. Keep teaching you all the 200 problems in the book until you get everything. Can't do that. Because why? The examination I will give you 201 problem, which you haven't done again. So you have to understand this. Right? Unfortunately, university I saw on the web, there was this guy who was written, I don't know, written saying that all the people who teach us are university lecturers from the state universities. In the state universities, they tell you something and then that's it, you learn. Then I'm telling you, yes, absolutely, I'm also doing the same thing. Yeah, I'm telling you something, and then A level, the teacher was to teach you. 15 questions on the same thing. I've seen, right? Until you have seen all the aspects of that single question, and then even if you in your dream, if somebody gives you a question, you know how to answer. You don't do it. Right? So why? Then you become idiots. Because then you are forced to know only one method or some method that I teach you. You can't do that. Because why? You go to the bridge, they ask you to build a bridge. You go there, see, I'm a civil engineer, let me do it. Go to the bridge. This doesn't look like the embankment. Look at the book. Embankment. The structure. This looks like a little. You say you can't build bridges like this. That's what you're going to say. You can't say that. Right? You're building a tall structure. You're going to say, in the course we have taught you up to 4 floors. This is 16 floors. You say, are you crazy? Only make buildings with 4 floors. That's what's going to happen. Right? Right? You're going to see the new building. No, you don't see the building. You have trouble in the new building. Because then they put the thing, they said, the background, whatever, the ground soil is not strong enough. I was thinking to myself, maybe you can get 4 floors. Finished. You want to build 14 floors. But the soil is not strong enough. So they are going to pile it in deep. China is going to 5 lakh. Then we create it. Let me show you the pictures. I'm surprised you guys have not seen this before. Here. You didn't see this before? No. Sad story. This is how it's going to look like from the angle. So we said we don't care even if you build it from China and go to I don't know, you can dig right up to Jupiter. The 14 floors have to come up because we don't have enough room. So they said, fine, we'll bring you the 14 floors. So this is what it's going to look like once it's built. Right? Different colors here and there, but this is how it's going to look like. There's going to be underground place here, right, under this thingy where you're going to have a stage and a huge student area. So Friday nights you can do. Right? 14 floors. All of these things are going to be lecture halls. They are going to push all the staff members right up to the top. Right? Because you can't do anything to the top. Right? Except for the auditorium. No, I think there's an auditorium on top. Over here. 2 huge auditoriums like this on top for the 2 things, right? So that's how it's going to look like in the future. See, this is you guys, see? Moving along. You see? That's going to come up that side. Right? Of course, we wanted, the old people, we wanted from the fifth floor of this to have like a skyway to the fifth floor of that. We told the MD we want a skyway to the thing, basically like the Petronas Tower in Malaysia. He said, out. Right? So there's no flyway. Yeah. And the car parks, and this is how it's going to look like. I think I have only 2 pictures, I think. Yeah, I got only 2 pictures. Right, so it's going to be very exciting. It's not going to get any easier in the course material as you go to level 3 and 2, but at least we have a nicer time inside the classrooms. Okay, done, finish. Let's get on to the next one. Here. Now we are going to get on to some very important stuff. Now here, I'm going to start teaching what I'm going to start teaching now onwards. Only a small amount of it is going to end up in your midterm paper. Right? Small amount. If I'm in a bad mood, maybe a little bit more than small amount. Small plus delta x. Right? Other than that, what I will teach you, because I understand it takes a little bit of time for you to absorb. So if I now do this teach and next week I will ask for examination, I know half of you are not going to answer. But I want to put some of it in there because I want to get the curve right. Good people, bad people, the bad people, nice curve. Right? So I'm going to put some of it in there so people who have picked it up quickly, I can separate out from the others in the system. Now what we are going to do is a very important part of our, that's my here. It's basically called, right, power calculations. Because why? If you take a look at AC theory, AC stuff, it's all about what? It's all about power. Right? Power, less power, more power, how to save the power. Even if you go home, it's what? Power. Switch off the light, no iron. It's all about how to manage that particular power. So we have to have some way of modeling this system. Here, we start off with everything we know. What is it? We say Vt is equal to Vm times like sine omega of t, and we said that It that looks a little wrong, right? Okay, so we will just look at this again. Okay, is equal to simple Im and sine of base omega t. Let's just look at this first and then let's go to the next one. Now if I want to calculate something called Pt, which is called what is instantaneous power, at that instant what is the power? That is equal to what? From your advanced level theory, it's Vt into It. Right? Vi. P equals Vi. You knew this. P equals Vi. Now, if it's P equals Vi, immediately we can write Vm Im times sine squared of omega t. Now, you tell me, where if I want to find the power, now this is instantaneous power. If I give you an interval of some interval of time, and it so happens to be, if this is a sinusoidal waveform, it so happens to be the fundamental interval of time. If I find the signal power in that whole area, what I find is the average signal power. Now, how do I find the average value of it? You integrate to find the area, and basically divide it by the interval, you get the average value. So, in your advanced level, I don't know whether you did it, but to find the average power, what we do is we take our signal through a single cycle of P of t. This is what this means. For a single cycle, I am finding the area under the graph, just adding up everything. Then this is the interval of time. If I want to write it like this, it's fine. Over t is going to be the base average power. Now let me ask you. If I ask you to draw t versus the P of t, tell me, what would this graph look like? What would this graph look like? Can you sketch it? Now you know the graph of V, you know the graph of I, you know that P is actually a multiplication of V and I. What would it look like? What would it look like? Just get it. Just. I'm getting a lot of stuff. What does it look like? Your head blew out. Good. That's it. Okay, I got the answer. Yeah, it's I squared. No. VI, not I squared. So this is what it looks like. Here, if you have, so let's say here, this is going to be V. Let's say this was V. The other one is also, I don't know, sinusoidal. That is I. If I just multiply these two, so I take this number 1 and 2. If I multiply, what do I get? Something like this. This side is 0. See, these both of them 0, 0. And here, this is minus. This is minus. Minus is what? Plus. So I will get something like this. So essentially, what I am doing is I am finding the area of this. Then this is t. I take the area and subdivide it by the t interval. I get the average value, which is the average power. So here, I just want you to see how it looks like, because I am going to use this fact as I go along. Now I just substitute this. What do I get? I get P average is equal to 1 over T going from 0 to T of VMIM and sine squared of omega t, right? dt. This is equal to what? 1 over t 0 to t Vm of an Im 1 minus cosine 2 omega t over 2 dt, right? Remember the identities, the trigonometric identities. Then this is equal to what? 1 over t going from 0 to t, right? In fact, I can take out the 2 also. 1 over 2t Vm dt. Then you got minus 1 over 2t going from 0 to t cosine of 2 omega t times dt. Right? Now I don't care if it's cosine 2 omega t or d omega t or I omega t, whatever the omega t is. If I get the average value of a sinusoidal signal, I will get what? Remember, you did this in your advanced level when you did something for the galvanometer. Did you do that? Yes, galvanometer. What do you see when you give it to an AC signal to find the average value? 0, right? See, you got galvanometer. Who cares? See, that taught you something. See, if I take a sinusoidal signal and over a particular interval of time find the average. This is plus, that is minus. When I add them up, what would I get? 0. Right? So this, go home and do it anyway and see. This would turn out to be 0. Also don't forget that 2 pi over t is what omega is, right? Otherwise you will not be able to do this. Then I take what I have here, I get what? 1 over 2t going from 0 to t of Vm Im dt. Now this Vm Im has nothing to do with the dt, so this is going to be 1 over 2t times Vm Im times t. That will give us Vm Im over 2. Right? Now this Vm Im is what? Vm Im was the peak value of the sinusoidal signal. Remember, peak value of the sinusoidal signal. Now we also understand, if I take a resistor of some sort, like a sort of a resistor, if I find the P average in the resistor, it will be what? VDC IDC. Right? We understand if you take a resistor, P. If you take a resistor, you can extend this to be what? Extend this to be V squared over R and I squared R. How do I do that? We know that VDC is equal to R times IDC. If I substitute here, this is also equal to VDC squared over R, right? And it is also equal to IDC squared R. So essentially, if I look at a DC, fixed DC value, it's Vi. Yeah, that's correct. It's Vi. Now, if I equate this, what I see up here, which is the AC, this is the AC signal average power, AC signal average power to some equivalent DC signal. So I would get, let me say, I call it VRMS and IRMS. Now both of them are DC values. It's like V times I. If I equate an equivalent DC circuit which has signal power VRMS, IRMS to this AC one, which is Vm times Im over 2, then this can be written as Vm over root 2 times Im over root 2. See, root 2 multiplied, you got 2. Then I can say that VRMS is equal to Vm over root 2 and IRMS is equal to simply Im over root 2. This is where that RMS value started. RMS is now what? Equivalent DC circuit that will generate the same signal power as the AC circuit. Did you see this? There you go. That's how the RMS came. Now this is of no use to you because you already know this equation, but you still are very happy because you know how this is now brought about. What is RMS? We have not explained RMS. Yes, explain RMS. Now I want to extend this slightly. Here's what I am going to do. I am going to tell you that V of t is equal to V of m times sine of omega t, and I of t is equal to I of m sine omega t plus some angle. Now remember, if it was a resistor, if you send V through it, you realize V and I don't have any angle difference. But if you did send a V to either an inductor or a capacitor, on the other side you would have got a phase shift of 90 degrees. Right? So let's consider some element, I don't care what it is, some element, when you send V through it, the I has a phase difference of phi. Some case. You know if it is inductor, that will be 90. Right? If it was a capacitor, that will be minus 90. What you get for phi. Right? But let's say it is this. Some element, I don't know what that element is, the V and I are phase shifted as it goes through. Now tell me, what is the instantaneous power? It is again VTIT. And it is again can be written as VMIM, but now this is going to be sin omega t plus phi. Now from a advanced level, you are going to get it. There is a trigonometric identity that says sin A plus sin B is equal to 2 times sin A plus B over 2, what? Cosine A plus B, minus B over 2. Use that here to split this up. Use that here to split this up. I want to show you something. I want to really show you something. Now here, you can use the expression. So I have already written it here. Sin A, sin B is equal to cosine A minus B cosine A plus B. If you feel that you don't know any of these things, A4 sheet on the side, write everything down. Right? Well, I might not ask you this, but anyway, good to be safe. Right? As an engineering student, one of the greatest things that I have learned when I was an undergraduate was how does an LED light. Is it? There was a subject for us called electrical properties of matter. We have seen LEDs. You give it 2 volts, it lights up. You give it 6 volts, it lights up and it burns. We have seen that. There, they showed me the equations, how this happens. As an engineer, I was thrilled. Right? Of course, we did all kinds of bad things about the lecture. But when we looked at it, I was happy because now I knew how the LED works. Right? So this is like that. That all these things that I'm teaching you is how it works. Nobody's going to ask you at the examination, tell me what is sin A plus sin B? What is the power? Nobody's going to ask you. Maybe they give you some, generators, lights and stuff like that, say the 5 is maximum signal power. But nobody's going to ask you these things. But I spend my time teaching you this because this shows you the way. Watch it. We need to know these things. Right? You know this. Page number 9. I will do this and I'll show you this and then we'll stop for a cup of tea. Now if I do this, I will get a P of t which is equal to Vm over 2, just like earlier, cosine of phi, right, minus cosine of 2 omega t plus phi. You can go home and see how you use this or that to get this. Right? But here's the deal. Now if I find the P average of this, by integrating this, you are definitely going to realize this part is going to go to 0. So if I am again going through a cycle of Pt dt, you are going to find out this is going to be equal to Vm cosine of phi over 2. That's what you're going to find. In fact, I would call this VRMS times capital IRMS. You can write this as V simple or capital, I don't care. Cosine of phi. So if there is a shift in the angle as it goes through this element, my P average is equal to V into RMS, I into RMS, cosine phi. Now this is a very important equation. Some people in the advanced level may have seen this. There are some very enthusiastic teachers who say to everything. But here's the deal. Can you tell me what happens to P average when phi is equal to 0? How much is it? Here. This is VRMS, IRMS. Right? If I change my phi to 30 degrees, is that P average going to be smaller than when phi is equal to 0 or bigger? Smaller. Smaller. If I make it 60, more small. If I make it 90, what happens? It becomes 0. What is the implication of this? Now the question you have to ask yourself, what is the implication of this? Each time in your home, if you put your washing machine, if you put your blender, you are making this phi bigger than 0. What's going to happen? You think, my goodness, this is brilliant. Because why the power consumed can be made 0 if I get you bring your blender to my house. Don't worry about it. Your washing machine, come and bring it here. Put all of the things which have inductive loads. Look at a machine, what you have? It's a coil. Coil is what? An inductor. You have yourself a blender, what do you have? A coil. Moment you put a coil, what happens? It's not a resistive load. You say, don't bring ions. Because what? It's purely resistive. Don't bring any of them. Motors are a bigger diameter. Bring it to my house. Because why? More and more you make it inductive, the angle increases, because if it's a pure inductor, how much is the angle? 90 degrees. Then what happens? No electricity. Perfect. No electricity. Then later, electricity company will say, this guy has a lot of motors and stuff. No electricity. You can't have this, no. Then they bought 2 machines. In fact, all industrial loads, industrial car, they can't get away like that. They have 2 loads, 2 meters. You have only one. They have 2 meters. The very first meter will measure something called the active power. That is when the P is 0. Right? Other one is going to measure the reactive power, which is that imaginary part that is not there. Will both. Then after the this is not good. Right? Then you know what they did? They said this is not very good, because why? Now I am getting 0 on the bill, but I am getting charged on the reactive power. They got smart. They said, no. Let me pay just like the households with less inductance. You know what they did? Since they had motors, they simply hooked up what is known as a capacitor bank right in front of the machine. Now, what happens? So, what will happen? Basically, the machine is what? Is inductive. See? I'll show you how it happens. We'll have tea and come, right? We'll have a cup of tea, we'll come back and revisit this. Right? Good.